Video 67 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is the Hallman-Feynman theorem for approximate wave functions. Approximate wave functions, as we have introduced them so far in this chapter 9, they all depend on molecular orbital coefficients and possibly also on some kind of configuration or determinant coefficients. Depending on the method, these determinant or configuration coefficients have different names. They are sometimes called correlation coefficients or amplitudes. Right now, I want to combine both the molecular orbital coefficients and these determinant coefficients. I want to denote them by this symbol Ci. Now, the energy of all the methods we have discussed, all the approximate methods, can be expressed or calculated as an asymmetric expectation value where I have different wave functions or where I possibly have different wave functions in the bra and the cat. In the variational methods, SCF, Hartree-Fock, MCSCF, and CI, this expectation value is symmetric, so we have the wave function in the bra and the cat are the same, whereas in the non-variational methods, Müller-Placid perturbation theory and coupled cluster theory, the wave function in the bra is different than the wave function in the cat, and actually in Müller-Placid perturbation theory, the wave function in the bra is often just the Hartree-Fock determinant, and in coupled cluster it can be the Hartree-Fock determinant or the Hartree-Fock determinant times e to the minus t. Now let us again consider a Hamiltonian which depends on some real parameter. That can be a change in the coordinate, it can be the strength of an external field, for example. Now, if the Hamiltonian depends on this parameter L, then of course the wave function will depend on it, and the dependence of the wave function on this parameter lambda will, for the kind of wave function we looked at, be because the wave function parameters, these coefficients C here, the molecular orbital coefficients and the determinant coefficients, depend on lambda, which is denoted in this way. In some cases, in addition to the molecular orbital coefficients and these determinant coefficients, actually also the basis functions could depend on the perturbation. This is, for example, the case in the popular gauge-including atomic orbitals, which are used for the calculation of magnetic properties like magnetizabilities or shieldings. However, in this presentation here, I will ignore this. So the basis function will be independent of the perturbation. Now, if you take now the derivative of the energy with respect to this parameter, then of course the energy might directly depend on the parameter. So I get here the partial derivative of the energy with respect to this parameter. But of course the energy depends on the coefficients, which as we know depend on the parameter lambda. So we get from the chain rule also this contribution where we have the derivative of the energy with respect to all the coefficients and then multiplied with the derivative of the coefficient with respect to the parameter lambda. Now, if we use the expression as we had on the slide before, where the energy is calculated as this transition expectation value, then the derivative can be written in this way, because the direct derivative of the energy is then actually the derivative of the Hamiltonian with respect to the parameter lambda. And the indirect derivatives which we have here are then the two terms where we have the derivative of the wave function with respect to the coefficients times the derivative of the coefficients with respect to the parameter lambda, and both in the bra and in the cat. So let's look now what happens for the different kind of wave functions. Now, the molecular orbital coefficients actually will be the same in both the bra and the cat wave function, although in Müller-Placid perturbation here in coupled cluster, the wave function is different, but the molecular orbitals will be the same. Now, let's look at variational methods where the wave function is variation optimized with respect to all parameters. Then the direct derivative of the energy with respect to the coefficients is 0, that's our optimization condition or variation condition, which corresponds to the fact that these integrals where we have the wave function in the bra or in the cat, the Hamiltonian, and then the derivative of the wave function in corresponding the cat or the bra, the derivative of the wave function with respect to molecular orbital coefficients, that these integrals are 0. That means that from the for the Hallman-Feynman theorem, for the derivative of the energy with respect to the parameter lambda, the only term which survives is the direct derivative of the energy with respect to lambda, which means the term which is the expectation value of the derivative of the Hamiltonian with respect to lambda. Which means that for variational wave functions, approximate variational wave functions, the Hallman-Feynman theorem actually is fulfilled, which means that the derivative of the energy with respect to a parameter lambda in the Hamiltonian is actually the same as just the expectation value of the corresponding derivative of the Hamiltonian with respect to this parameter lambda. So for SCF, meaning Hartree-Fock, and MCSF wave functions, the Hallman-Feynman theorem is fulfilled. It's also fulfilled for the full configuration interaction method. But for truncated CI methods, it is actually not really fulfilled because the truncated CI wave functions are not fully variational optimized because the molecular orbital coefficients in a configuration interaction wave functions are not optimized. It's just Hartree-Fock molecular orbital coefficients, and therefore the derivative of the energy with respect to the Hartree-Fock coefficient, the CI energy with respect to the Hartree-Fock molecular orbital coefficients, is not going to be 0. In the limit of a full configuration interaction wave function, however, it is again fulfilled. Now for non-variational approaches, as Laplace perturbation theory or coupled cluster, the derivative of the wave energy with respect to any of the wave function parameters, molecular orbital coefficients or correlation coefficients, amplitudes, is not 0, and therefore the Hallman-Feynman theorem is in this way not fulfilled. However, one can choose the wave function in the bra in such a way that the Hallman-Feynman theorem anyway is fulfilled. The only condition, of course, is that one still has to get the original energy back. But there are some degrees of freedom which one can use so that one gets the Laplace perturbation theory energy or the coupled cluster energy as the expectation value of the Hamiltonian, but still the Hallman-Feynman theorem is fulfilled. Such an expectation value, transition expectation value, was defined by our opponent for the coupled cluster energy, where the wave function in the bra is called the coupled cluster dual bra state or just the lambda state, and it's defined in this way. So it's not just SDF, but it's SDF with here the lambda operators, and then afterwards the e to the minus t operator again. And the lambda operator is the same lambda operator which we had in the chapter about excitation and de-excitation operators. So it's the sum of all the de-excitation operators. Defining the coupled cluster energy in this way, or calculating in this way with this dual state or lambda state, the Hallman-Feynman theorem is then fulfilled, at least partially fulfilled, meaning it is fulfilled with respect to the coupled cluster amplitudes. Now this is historically came this expression first, but later on one figured out that this transition expectation value is just an example for the much general concept of Lagrangians for non-variational wave function. Lagrangian is a mathematical tool which one in general can use if one wants to optimize some mathematical function, where at the same time some extra conditions have to be fulfilled. In our case, this mathematical function, of course, is the energy, or the expression for the energy, which we would like to be variational so that the Hallman-Feynman theorem can be fulfilled. But we have the extra conditions, which are the equations from which we have determined the wave function parameters, and they also have to be fulfilled. So these are the extra conditions which we have in our case. Now, the Lagrangian then in general is defined in the way that one takes the function which one wants to make variational, and then one adds the extra conditions which have to be fulfilled in such a way that they are zero. Now, in the case of the coupled cluster vector function, this is easy because they are anyway zero. So one adds essentially zero to the energy here, which means we don't change the energy. But one adds all these conditions multiplied with some new parameters, some new variables, which are called the Lagrangian multipliers. Doing precisely that for the coupled cluster, Lagrangian actually turns out that our opponent's expression for the coupled cluster energy as this transition expectation value is actually just the Lagrangian for the coupled cluster wave function. So the Lagrangian multipliers, lambda, as I indicated already by using lambda as a symbol for the Lagrangian multipliers, are actually just the amplitudes of the lambda or dual state. So the lambda or dual state is just a convenient way of writing or building in the extra condition, the extra constraints into the expectation value expression for the energy. Now, one has now additional set of parameters, these lambda amplitudes, and therefore our Lagrangian has to be now stationary with respect to the original amplitudes in our wave function and to these new amplitudes. But the derivative of the coupled cluster Lagrangian with respect to these new lambda amplitudes is trivially zero, because if you take the derivative of the Lagrange with respect to the lambda amplitudes, you just get your coupled cluster vector function, the equations for the coupled cluster amplitudes back, and they are, if we have determined the amplitudes, coupled cluster wave function amplitudes from this equation, they are just zero. So this is trivially fulfilled. But what about the derivative with respect to the coupled cluster amplitudes now? Because the coupled cluster energy itself is not variational with respect to the coupled cluster amplitudes, but what about the coupled cluster Lagrangian? Now, taking the derivatives with respect to of the coupled cluster Lagrange with respect to the coupled cluster amplitudes then gives this expression here. And this expression includes the lambda amplitudes, and we have not yet determined what the lambda amplitudes are. So these actually are the equations for the lambda amplitudes, and it has to be zero, because then the coupled cluster Lagrangian is variational with respect to the coupled cluster amplitudes. So one gets a new set of equations for these lambda amplitudes. So having solved the equation, the coupled cluster equation for the T amplitudes and the coupled cluster, these new equations for the lambda amplitudes, then the coupled cluster Lagrangian is variational or stationary with respect to both the coupled cluster amplitudes and these new lambda amplitudes. And therefore we can take now the derivative of the energy with respect to the parameter lambda in the Hamiltonian, meaning the derivative of this coupled cluster Lagrangian, and it will turn out that this is then just the expectation value of the derivative of the Hamiltonian with respect to lambda. I've illustrated the idea of this Lagrangian now for the coupled cluster wave function, the coupled cluster energy, but one can define a corresponding Lagrangian also for the Möller-Blessed second order or higher order energies, and then derive also expressions which will fulfill then in this way the Hallman-Feynman theorem also for Möller-Blessed perturbation theory. This approach for calculating first derivatives of the energy as expectation values is called the unrelaxed approach, which essentially is a nice word for saying that the Hallman-Feynman theorem in reality is still not really fulfilled. The problem is that we now, by making this Lagrangian for either coupled cluster or for Möller-Blessed perturbation theory, we have taken care of that the original coupled cluster energy or Möller-Blessed perturbation theory energy was not stationary with respect to the correlation coefficients or the amplitudes. But we have not taking care of the fact still that the energy is also not stationary with respect to a change in the molecular orbital coefficients. Now one can also include that, and that then will lead to what is called the relaxed approach. So one can also write up a couple cluster Lagrangian, which then also will be stationary with respect to the molecular orbital coefficients. And one calls this that one includes the orbital relaxation, meaning the orbitals will change due to the value of the lambda parameter. And for the couple cluster wave function is written up here. So I get now, in addition to the exponential operator with the t operator, I also get an exponential operator with the kappa operator, which is the orbital rotation operator in all the terms. And these are now the conditions again for the t amplitudes. So that's the couple cluster vector function again, here with the lambda parameters, which are the Lagrange multipliers for the derivatives with respect to the t amplitudes. And we also get another set of constraints, which are the constraints for the molecular orbital coefficients. And we get a new set of Lagrange multipliers, which make sure that then this relaxed couple cluster Lagrangian also will be stationary with respect to the molecular orbital coefficients. And for these Lagrangian, the Hallman-Feynman theorem will then be exactly fulfilled for all the wave function parameters. To conclude this chapter, let's look at the second derivatives of the energy for approximate wave functions. Taking the first derivative of the energy with respect to lambda gave us two terms. It gave the direct derivative of the energy with lambda, and then from the chain rule, it gave us a term where we had the sum over all the derivatives of the energy with respect to the wave function parameters times the derivative of the wave function parameters with respect to lambda. And now we have to take once more the derivative with respect to lambda of that. So again, we will then, the direct term, we just get the second derivative of the energy with respect to lambda. And from the other term, because of the chain rule, we will get three terms. We will get, because it's a product, so we will get the derivative of the first term in that product, where we take the derivative with lambda. We will get a term where we take the derivative of the second term with respect to lambda. And then again, we have to take the chain rule again with respect to the energies. So we get the second derivative of the energy with respect to the wave function coefficients times the square of the first derivative of the wave function coefficient with respect to lambda. So that's for the general case, meaning for the non-variational wave functions. For the variational wave functions, again, we can make use of the fact that the first derivative of the energy with respect to the wave function coefficients is going to be 0, which means that the last term here will disappear, and we are only left with the first three terms. But there's no further way to get rid of more of the terms. So one has to evaluate here then not only second derivatives of the energy, mixed one with respect to molecular orbital coefficient and lambda, and the second derivative with respect to molecular orbital coefficients, but one has to evaluate also the derivatives of the wave function parameters with respect to the lambda, which are called the response equations.